Thank you guys for joining for this new edition of the research seminar here in the ModMat. Today we have the talk of Florian Wechsung from the Koren Institute in NYU. Florian is a postdoctoral researcher in the group of Universidad, you just here. And today he's going to talk about these preconditioners for steady incompressible flow based on augmented Lagrangian technique. So Florian, welcome. Thank you again for accepting our invitation. And well, the Zoom is yours.
Awesome. Thank you. Thank you again for having me, and thank you all for joining today. So this talk is kind of a summary of 2 or 3 years of work, and I'm trying to focus on some key ideas here. And I sort of I'm skipping a lot of the technical details. I have some references at the end, and I'm happy to answer technical questions if anybody has them. But I'm really trying to keep the focus on sort of high-level ideas here. And the goal of all of this is to develop fast and scalable solvers for problems such as the incompressible Navier-Stokes equations. But hopefully I'll be able to motivate why the same ideas can be used for other equations. So before I begin, this is a joint work with Patrick, who is my PhD advisor, and then Lawrence, who's at Durham, Ridgway Scott, who some of you may know at Chicago, and then Georg Stadler, who's my boss now, and then Jing Min and Melody were students who helped with this, and then Jessica is a collaborator of mine who is now at MIT. And so if you're in the business of sort of applied math, then you'll have noticed that there's a lot of physical systems that can be described by PDEs that are of the nature of you have some sort of governing equation and then some constraint, right? So let me give you some examples. So for Navier-Stokes, you have your momentum equation, and then you have a constraint that your liquids should be incompressible, for example. Or for magnetic fields, you have the Gauss law that again tells you that the divergence should be 0. Or if you're modeling liquid crystals, then you are usually solving for the direction of the crystals, and then you have a unit length constraint for that direction vector. Or if you're doing elasticity and you want to enforce exact incompressibility of the deformed domain, then you have a constraint on the determinant of the identity plus the Jacobian of the deformation, right? And so this sort of pattern of having an extra constraint in your equation is pretty frequent. And so what I'm doing today focuses on the case of the Navier-Stokes equations, but some of these ideas can be transferred. And I give some references at the end for papers where we transfer these ideas. And so just to set the scene, so the equations that we consider are the stationary Newtonian and incompressible Navier-Stokes equation. So we have our momentum equations here. We have some diffusion and some advection. And then we have this constraint that the divergence of the velocity field should be 0, right? And we just assume that we're given some suitable boundary conditions. And so if you've done any sort of fluid dynamics before, then you know that the behavior of these equations and the behavior of any fluid is really governed by the so-called Reynolds number. So the Reynolds number is the ratio of the characteristic velocity and length scales and the viscosity of the fluid, right? So if you have something that moves very fast over very long length scales, the Reynolds number is very high. If you have something that's really, really viscous, like honey or lava, then the Reynolds number is pretty low, right? And in this talk, the regime that we're interested in is sort of the regime of Reynolds number 10 to 10,000. Okay, so this is the regime where steady solutions still exist or are just about to stop existing. And you may have sort of multiple solutions, and classical solvers start to struggle. And so in general, with the Navier-Stokes equation, in almost every way, life becomes harder as the Reynolds number increases. Right. So if we look at the first equation, we see immediately that, okay, so the Reynolds number increases, which can be seen as the viscosity decreasing, which means that this term becomes smaller and this term here dominates, right? So we immediately see from looking at the equations that they become more nonlinear as the Reynolds number increases. You can also show that the error between the exact solution and then whatever you use to approximate it becomes larger when you use standard discretizations, right? So think of like a Taylor-Hood discretization. If you ever solve the Navier-Stokes equation using finite elements, the error blows up as you increase the Reynolds number. And then finally, okay, so the system is nonlinear. How do we solve a nonlinear system? Well, usually we use Newton. If we use Newton at every step, we need to solve a big linear system. These linear systems become harder and harder to solve as we increase the Reynolds number. All right. And so in this talk today, I'm not going to discuss the first 2 points. Those are hard and sort of deserve their own talks. I'm solely going to focus on how do we solve these linear systems at every Newton step, right? Okay, and so just to as a last bit of motivation, to really drive home the point that it's the Reynolds number that drives the whole nature of the flow. We have, this is an experiment that Jess did, where we sort of compare an experiment with some simulations at different Reynolds numbers, and only increasing the Reynolds number from 7 to 34 already totally changes the nature of our flow, right? For 7, it's nice, it's symmetric. For 34, suddenly it becomes the solution becomes non-symmetric, which tells you there is at least one more solution if you just flip it vertically. Yeah, it's totally changed the nation of our solution, right? And in fact, solving these equations, even just for Reynolds number 34, is already much harder than for Reynolds number 7. It's also just nice to see that that our numerical simulations actually line up with what you see in a lab, right? I'm someone who never steps into a lab, so when she showed me these pictures, I was very happy that, okay, our solvers don't just produce pretty pictures, but actually it lines up. Okay, so when we're solving PDEs using the finite element method, what we do is we put our problem into the weak form. And so how do we get the weak form of our PDE? We multiply with a test function. We perform integration by parts. That's our weak form. So the problem we're solving is, again, we have our diffusion, we have our advection, and we have our divergence constraint, right? And we've picked some spaces VH and QH for the velocity and for the pressure approximation. All right, so these are finite dimensional spaces, and this is the standard sort of Galerkin approach to solving PDEs. And we can't just pick any spaces. These spaces need to satisfy a certain condition, the so-called inf-sub condition. Essentially, what this means is that the velocity space needs to be large enough, or phrased differently, the pressure space can't be too large. But that's not crucial to this talk. Okay, so the strategy for today is I'm going to talk a little bit about block preconditioning. Block preconditioning has been around for a couple of decades, and it's one of sort of the go-to approaches for any sort of mixed systems. And then I'll motivate this augmented Lagrangian approach, and I'll try to give some intuition why that should be a good idea. And then this augmented Lagrangian approach will require us to develop a new multigrid system to work well. And then at the end, I'll show some numerical results. Okay, so we have the Navier-Stokes equations. We bring them into weak form. We discretize using the standard Galerkin approach. And so once you do all these things, and you write it out as you write the linear system out in matrix form, what you're given is a system that looks like this. So it's a system in velocity and pressure. And we have, again, our diffusion plus advection term, and then we have the matrix B that enforces our constraint, right? And this is of saddle point-like form. And solving saddle point systems is usually pretty hard, it can be hard, and especially when you have a huge number of degrees of freedom, right? And so what we're thinking here is like hundreds of millions or billions of unknowns. And if you have that many degrees of freedom, you can't just use a direct solver, because they just scale so poorly that this would it would run out of memory. You wouldn't have enough time. It's just completely infeasible. And so what we want to do is we want to use an iterative solver. And for an iterative solver to be successful, we need a preconditioner. All right. So if you want to use conjugate gradients or GMRes to solve a system like this, we need a good preconditioner for our linear system. And a preconditioner is essentially a matrix that is cheap to evaluate and approximates the inverse of this Jacobian. And so for these block systems, one of the key insights for developing preconditioners has been the following. We can do a symbolic factorization of this matrix. And it turns out that this triple product here is equal to the inverse of the Jacobian, right? So what do we have here, or what appears in this triple product? We have two triangular matrices, and we have a diagonal matrix. And the sort of blocks that pop up are this A inverse 3 times, and this S inverse. Right? And so the name of the game in block preconditioning has been for several decades now that you try to find approximations, which we call A hat and S hat, for this matrix A inverse and S inverse. And if they are good approximations, then the hope is that the resulting triple product is a good approximation to the inverse of J. Right? So just to summarize, we have our Jacobian J that we try to approximate. We have an explicit form for the inverse, but it contains sort of difficult matrices. And so we approximate these difficult matrices with something simpler, and one can do some analysis to show that this approximation is still good, right? And so let me give you some examples. So this is our triple product, and somebody gives us a PDE, let's say the Stokes equations, and now we need to tell that person, okay, how do we approximate A hat, and what do we choose for our A hat and S hat, right? And so for the Stokes equations, a major achievement by Andy Wathan and David Sylvester was that they realized that if you just use a cycle of multigrid for A hat and a pressure mass matrix for the Schur complement, then you get an approximation, and you get a preconditioner with mesh-independent iteration counts. What does that mean? It means that as you refine your mesh, the iteration counts, the number of steps you need to find your solution stays constant. But if you apply this preconditioner to the Navier-Stokes equations, the iteration counts actually blow up with Reynolds number squared, right? So for Reynolds number 100 or 1,000, which is what we would like to do, iteration counts are already massive. Okay. A couple years later, this was improved, and they realized, okay, if they choose a different choice for the Schur complement, this matrix S, again they get something that's mesh dependent, but iteration counts only increase like the square root of the Reynolds number, right? And so that's a massive improvement compared to quadratic growth, but it's far from ideal. So here's an example. So this is sort of using existing codes that were published by the authors of the previous paper for one of the standard benchmark problems. And so as we go down, we make the mesh finer. So we increase the number of degrees of freedom, and iteration counts, they increase slightly, but they're essentially constant. So that's fantastic. But as we increase the Reynolds number, the iteration counts blow up. Right, so for Reynolds number 5,000, we need 500 iterations to find a solution. And so actually, if you can run the same experiment using an exact solver for A inverse. And that means that the key difficulty here lies in approximating this Schur complement approximation. And I just want to go back to drive home this point. So we in the block approximation to the Jacobian, we make two approximations, right? We approximate A inverse and we approximate this S inverse, where S is the Schur complement given by this triple product. And it means that if we're using an exact solver for A inverse, but some approximation for S, and the algorithm fails, then it's the approximation to S that is our problem, right? Because everything else in the pipeline was exact, right? So we have clear proof that it's the difficulty lies in approximating the Schur complement when trying to solve the Navier-Stokes equations. Okay, so how can we make it easier to approximate this matrix S, this Schur complement? How can we find a better preconditioner for the Navier-Stokes equations? And so I want to motivate this by just looking at the Stokes equations, and then we'll apply the same trick to the Navier-Stokes equations, and we'll see in the numerical results that it still works. So the Stokes equations one way of deriving them is to write them as the minimizer of an optimization problem, right? So if you minimize this energy subject to this constraint, then if you sort of write the optimality conditions to this optimization problem, you get exactly the Stokes equations, right? You introduce a Lagrange multiplier that ends up becoming the pressure, and this results exactly in the Navier-Stokes equation. And so even if let's say you've never solved a PDE in your life, and you're, let's say you're an optimization person, and I give you this problem, and I give you this equality constraint, then a first idea for how you solve this problem would be that you might add a penalty to your objective in order to enforce this constraint, right? And we immediately see that, okay, adding this penalty here does not change the minimizer, right? Because we require that this is exactly equal to 0. And so at the minimizer, this is 0, and this doesn't change the solution to our system. But by introducing this term, we include this constraint weakly into the objective itself, right? So this is sort of a very natural way of dealing with an equality constraint. You add a penalty to the objective that you're minimizing. Okay, that's just saying what I already said. So adding this extra term doesn't change the minimizer, but makes enforcing the divergence constraint easier. And so the continuous version of this, so that if you apply this to the optimality conditions, then if you sort of look at this and apply the same idea to the Navier-Stokes equations, it's the following. So okay, so these were our previous momentum equations for the Navier-Stokes equations, and we add a term which we call the grad diff term, right? It's the gradient of the divergence of U. And again, we see that this doesn't change the solution of our equations, right? We already require this constraint, the divergence of U is 0. So adding this extra term here does not change the solution to our equations. The discrete version of this is that you add this matrix triple product to the saddle point system that you're solving, right? Again, sanity check. We're already enforcing that B times U is equal to 0. So adding this term here doesn't change a thing, because B times U would be equal to 0, right? So why bother, right? Why do we make this modification? Well, it turns out that this Schur complement, which was this sort of magical matrix that appeared when doing the Jacobian factorization, and of which we say it's really, really difficult to approximate, that the Schur complement of this new matrix is simply the Schur complement of the old matrix plus a mass matrix, right? And mass matrices are easy. They're the identity of finite element methods. So the good news here is that the Schur complement becomes increasingly easy to approximate as we make this term gamma large, right? So this is easy to see. If you make gamma large, then this Schur complement is entirely dominated by this mass matrix, and mass matrices are easy to do essentially everything with. Now, the bad news is, and I mean, we knew there had to be some bad news. There's always conservation of misery, that solving systems that involve this top left block becomes increasingly difficult, right? So previously, for this matrix A, we would just use one cycle of multigrid. It was super easy, but I will show you in a little bit that it's now much harder to solve this equation. So we've kind of shifted the difficulty, right? So the Schur complement is now easy, but the top left system is difficult. And just some numbers to back the statement up is, so if we just use an LU factorization for this, so an exact solver, then our iteration counts sort of nicely decrease as we increase gamma. Everything works exactly as we expect it to. The Schur complement approximation becomes really good. We combine that with using an exact solver for this, perfect. But if we keep using multigrid, then the iteration counts blow up. And that's simply because this matrix here is really, really difficult to invert. But we don't want to use an exact solver. We can't afford to use LU for a system of 1 billion degrees of freedom. And so the key challenge with augmented Lagrangian work is to find a fast and gamma robust solver for this matrix A. Okay. And essentially, that's what we're doing for the rest of this talk. We'll find a multigrid method that works robustly for this top left block. Okay, so as I hinted at earlier, we're going to do this for the Stokes equations and then see that numerically it still works for the Navier-Stokes equations. So we ignore advection. We set the viscosity to 1, which means that the top left block is now just the diffusion term plus this gamma times diff u diff v. Okay, and so the colors here are on purpose because this diffusion term, it's maybe the second nicest thing after a mass matrix that we can think of. It's symmetric, it's positive definite, standard multigrid works well. And now this term, it's again symmetric, but it's only positive semi-definite, right? It has a huge null space. Any vector field you throw in there that is divergence-free disappears in this term, right? And we know from numerical linear algebra that any matrix that has a large null space essentially isn't great for us. And so the sum of these two systems becomes what we say is nearly singular as gamma goes to infinity, right? Because this matrix with the huge null space dominates. So how do we solve a nearly singular system is the question. Okay, so here's our wish list. And the three things we want is we want good performance, even for large values of this penalty parameter gamma. We want linear complexity in the problem size, right? So you double the degrees of freedom, you only want to double the runtime. And we want to develop an algorithm that works well in parallel. We want to run this on big supercomputers with tens of thousands of cores. So LU factorization ticks the box that it's robust. Unfortunately, it scales polynomial in the problem size. And the parallel performance, it kind of depends on the implementation. It scales well to a couple of hundred degrees of freedom, a couple of hundred cores, but not well into the tens of thousands. Standard multigrid has linear complexity, great parallel performance. It's used on every HPC system in the world. But we saw earlier that as you increase this penalty parameter gamma, the iteration count blows up. And I'm not going to go into the details of multigrid here, but essentially all you need to know about multigrid for this talk, and this is a vast simplification, is that you approximate your solution on the finest mesh by first starting on a very coarse mesh, transferring the solution onto a slightly finer mesh, You do some smoothing on the finer mesh to improve the accuracy of your solution. You go to the very finest mesh, you do some smoothing again, and that's how you find your solution. Again, it's a vast oversimplification of how multigrid works, but it's all you need to know to sort of get the idea for the next couple of slides. And so Schur showed a good 20 years ago in his PhD thesis that if you want to build a multigrid scheme that is robust, the two ingredients that I just named, which are the smoothing on every level and then the transfer, that those two ingredients both need to be robust, right? So their efficacy shouldn't degrade as you increase your gamma. I mean, that's a very intuitive result, but he proved that that's correct. And so essentially what we're going to do now is we're going to attack both of these issues, the smoothing and the prolongation, and we'll show the impact of that on the iteration counts for solving this nearly singular system, right? So this is standard geometric multigrid. It is robust as you make the mesh finer, but the iteration counts blow up as you make the system nearly singular, right? So this sort of standard behavior, if you've ever tried to use multigrid to solve an elasticity equation of a material that's nearly incompressible, then you face exactly this problem. And so we want to improve on this part of the table, essentially. OK, so let's take care of the smoothing first. And so the concept that we're going to use here is this concept of subspace correction methods. And it's sort of an abstract framework that actually encapsulates a whole bunch of different approaches for building preconditioners. And some of the preconditioners that you already know can actually be described by this framework. So what you do is you look at your velocity space VH, and we consider a set of subspaces VI that if we take them together, they build this global space VH, right? And so those spaces VI don't have to be disjoint. There might be overlap between these spaces, right? So you could think of, you have a big mesh, and then you sort of take the degrees of freedom on the left. Those make up your space V1. You take the degrees of freedom on the right. Those make up your space V2. And the idea of subspace correction methods is now that you somehow solve the problems on each of the spaces VI separately, and then you have to combine the solutions again. And you are able to prove that if you do this in the proper way, then that's a reasonable approximation to the global problem, right? So you solve on smaller subspaces, you put the solution together, and that should be an approximation to the true global solution. And just as an example, so the standard Jacobi smoothing that many of us know would just correspond to, you pick a basis for a space VH for each of the degrees of freedom in your, like one basis function associated to each of the degrees of freedom in your mesh. And then each space VI is just the span of this single basis function, right? It's kind of a trivial example. Each subspace is only one-dimensional, but it's just to show you that the standard Jacobi method can be written in this framework. We're going to use different subspaces. And just as a pictorial representation, so here's a simple mesh that has 6 elements, and we have a second order basis functions on this mesh. So the Jacobi method would be each degree of freedom induces one of the subspaces. So here we have, I don't know how many, about 20 subspaces, all one-dimensional. And here's a different approach where we collect several degrees of freedom into one subspace. And on the right, we have a 7-dimensional subspace, right? And so the intuition here is kind of, OK, if your subspaces are very small, then probably all the individual solutions are very far away from the true solution, right? Because you've made such a massive simplification. But they're very cheap to solve, right? I mean, inverting a linear system in one dimension, which is the case for Jacobi, is just you divide by a number. That's cheap, right? For the vertex star, OK, the domain is a little bit bigger, so you kind of hope that it's a better approximation to the global problem. But then now you have to solve a 7-dimensional system, right? So we want to find the balance of, we want to keep the spaces as small as possible, but still good approximation quality. And one can essentially prove what exactly the smallest possible size for these subspaces is. Okay, and so the way we do this is we try to understand why Jacobi smoothing fails. And that's going to essentially tell us what the constraint is that we need to require for our subspaces. And so Jacobi smoothing is essentially just using the diagonal of your matrix as a preconditioner, right? And so if you've done any preconditioning before, if you want to get an idea for how many iteration counts is conjugate gradients or GMRES going to need, what you want to do is you need to relate the norm induced by your matrix and the norm induced by your preconditioner to each other, right? You want to bound one by the other. You want to, if you can show that these two norms are equivalent, then you know that you get good convergence. Okay, so what's the norm induced by our matrix? Well, it's just the norm of grad u plus gamma times the norm of diff u squared, right? So just as a reminder, the linear system here was grad u grad v plus gamma diff u diff v, right? So the norm induced by this, by the matrix corresponding to this bilinear form is just the norm of grad u squared plus gamma times the norm of diff u squared. Okay, so what is the norm of this operator that's just the diagonal of A? Well, it's essentially the same thing, but we compute this grad ui squared plus gamma diff ui squared for each of the individual basis functions, right? And we take the sum over all these basis functions. Okay, so why can these two norms never be equivalent? Well, think of a function u that is divergence free, right? And which means that this is now going to be 0. Now you split your function, your global function is divergence free, and you look at all the individual contributions of the basis functions on your mesh. Those are the ui's. No one guarantees you that those are individually divergence free, right? So this term here might be non-zero. Now multiply with a large value of gamma, this whole thing might blow up, right? So we can never hope to bound this norm by this norm in some way that doesn't depend on gamma. And that's exactly what I'm saying in this red box. So we essentially have no hope in general to bound this norm by this. But this problem already tells us the solution, right? The solution is that we need to find subspaces Vi so that if U is divergence free, we can find the decomposition into smaller functions Ui that are also divergence free, right? So the analysis for the Jacobi problem, for the Jacobi smoother, tells us what we need to require from our subspaces in order to make this work, right? So we need to select subspaces Vi so that if you have a divergence-free vector field U, you can find the decomposition into functions Ui so that each of those are divergence-free and they sum up to your original function U. And so we call this a local decomposition of divergence-free vector fields. And you can show that if this is satisfied, then your smoother is robust with respect to gamma. Okay, and how you choose these subspaces is highly dependent on your mesh. And so I'm just going to tell you for a couple of examples what these subspaces look like. So for a standard second order distribution in 2D, what you do is you take each vertex in your mesh, and then you collect all the degrees of freedom that touch this vertex, right? So you have something like, okay, 7 degrees of freedom, but it's a 2-dimensional velocity field that you're solving for. So you have like a 14-dimensional subspace around each of your vertices. Now, in the last couple of years, these barycentrically refined meshes have gathered some attention. They have some nice properties. For example, they enforce the divergence constraint of your problem exactly. But for these meshes, you need to take much, much bigger subspaces, right? So you essentially take your mesh, you barycentrically refine, you have all these degrees of freedom, and then you need to collect all of this, right? So very quickly, you have a subspace that's like 50-dimensional, right? And then recently, so this was done with a student here, Melody. She has been looking at quadrilateral and hexahedral meshes, and the result is very similar to that, to those meshes where, again, you look at a vertex and you collect everything in the cells that touch this vertex, right? And this theory is incredibly sharp. So what we've done is we've just made these patches a little bit smaller, right? So for example, you could say, hey, let's exclude these 3 degrees of freedom, and let's just make the patch a little bit smaller. It makes the local system cheaper to solve. It stops working, right? So the theorem on the previous slide is incredibly sharp. And so what happens if we take our multigrid and if we now use these block smoothers? We solve, instead of just on a single degree of freedom doing Jacobi, we take bigger patches and we solve on those. It seems to help massively, right? So we can now go to gamma values of 10,000 for very small iteration counts, but it's not quite perfect, right? We still haven't achieved full robustness. Eventually, iteration counts still blow up, right? So the second ingredient of multigrid, prolongation, is the thing that's still missing. Okay, and it turns out the problem is extremely similar. And the key thing will, again, be dealing with the divergence. And so to understand why the divergence is a problem, let's take a function on a coarse grid. And so let's say this is our coarse grid solution to the Navier-Stokes equation. Now we want to transfer this solution to the next finest grid. And we call the operator that does this transfer pH, the prolongation operator. And you can show that the norm that you care about is the energy norm associated with the PDE. So in our case, it's again grad u squared plus gamma div u squared, right? And so again, we want to relate this norm on the coarse grid to the norm of the prolonged function on the finer grid. And we have the exact same problem as before. We might have a function that is divergence-free on the coarse grid, might satisfy div u equal to 0. But now as we transfer it, nobody guarantees us that it's still divergence-free on the fine grid, right? So it could be either that you introduce some interpolation error going to the finer grid, or it could be that the notion of what it means to be divergence-free changes. By that I mean, if you have a finer, if you only enforce discrete divergence freeness by testing against some pressure test functions, if your mesh becomes finer, that constraint becomes stricter because you're testing against more functions, and again, it fails. So if this function phu, if this prolonged function is not divergence free, we cannot expect to bound this norm by this norm. But again, the problem tells us the solution. We need to modify the prolongation operator so that we're still divergence-free on the finer mesh. And OK, I'm just going to give some intuition for why that's the case. So this is for the simple case of your pressure space are constant functions, which means that the discrete divergence is essentially the same as just measuring the net flux across the facets or the edges in your mesh, right? So essentially what you're requiring is that if this is a cell in your mesh, the inflow and outflow across these edges here sums up to 0, right? That's all you're requiring. OK, so we refine this red mesh to get the black mesh. And so if the interpolation here is exact, it means that the flux across these facets is still exactly the same as before. And so what we can do now in order to make sure that the flux on this cell on this cell, on this cell, and this cell, still all adds up to 0, you can solve little Stokes problems to figure out what should these values here be so that all the fluxes sum up to 0, right? So you solve a very tiny local problem in order to figure out, okay, how do I modify my prolongation operator to ensure divergence freeness on the fine mesh? And okay, so there's some details which I'll ignore, but it turns out, okay, it works wonderfully, right? So we can now go to values of 10 to the 8, and our preconditioner converges in between sort of 3 and 6 iterations for everything. We've made our solver more expensive, right? Because, I mean, we have added extra steps to the prolongation, and the smoothing is now solving small linear systems instead of just doing Jacobi, which is inverting a number. But the benefit of this more expensive multigrid scheme is incredible robustness with respect to gamma, right? And so for large values of gamma, this pays off. Okay, and just to wrap up, let me show you the sort of the big picture again, and then show you that this works when applied to the Navier-Stokes equations. So we implemented all of this in PETSI and Firedrake. So Firedrake is this finite element solver developed at Imperial and Durham. It's very similar to Phoenix, which some of you may know. And it makes implementing these really nested and sort of more complicated solvers and preconditioning schemes very easy. So the full solver is, we have continuation on the outside, which means that we start with small Reynolds number, we solve, we increase the Reynolds number a little bit, we solve again, we increase the Reynolds number a little bit. Each of the nonlinear systems is solved using Newton. The linear system is solved using flexible GMRS. And then we have this block preconditioner that I explained at the very beginning. We use our approximature complement inverse, which is very similar to the mass matrix. We know that that works well. And then here we have our custom multigrid scheme, which has this custom prolongation operator, that's the transfer, and the custom smoothing, which is this subspace correction method, right? And all of that is available open source and online. And so there's two standard benchmark problems. There's a lid-driven cavity at the top, where you have a 0 velocity on these 3 walls, and then a horizontal velocity at the top here, and that results in the liquids kind of doing this. And then the other benchmark problem is this backwards facing step. We have 0 velocity here, we have an outflow here, and we have prescribed inflow velocity profile here. And we look at Reynolds number ranging from 10 to 10,000. So at Reynolds number 10,000, I mean, you're way beyond the point of stable, steady solutions. But for bifurcation diagrams, for example, it's still interesting to be able to compute these, even if they're not stable. And we can see that our iteration counts, especially for very fine meshes, when we go from like 2.5 to 8, or here we go from 3 to 6. So we don't get perfect robustness, which we got for Stokes, but extremely mild iteration growth, right? If you remember the results I showed earlier for the existing preconditioners, we're over 500 in this column already. And then we looked at a 3D version of this problem. It's essentially just an extruded version of this cavity and the backwards facing step. It just looks a bit more exciting. And we haven't been able to push the preconditioner all the way to 10,000, but up to 5,000, we see essentially robust iteration count. So we go from 3.5 to 5 here, or from 5, 3, 6, 4. So again, essentially constant iteration count. Okay, and so to summarize, so there was 2 key ideas here, right? So the augmented Lagrangian, the point of that was that you want to simplify the approximation of your Schur complement, but it makes it much harder to approximate the top left block. And in order to fix this, we have to develop Oh, and if I didn't make this, I don't think I made this clear enough at the beginning. So this augmented Lagrangian idea, this is not an idea that we had. This is an idea that Michele Benzi and Maxim Olshansky had in 2006. I think I cite this paper, but I don't think I made it explicit enough. Our contribution is really on this multigrid scheme. I should be transparent about this. So to solve this difficult top left block, you have to develop this multigrid scheme. And the two ingredients for this multigrid scheme are this smoothing and this prolongation operator. And the key thing to develop both of these is that you really want to understand what this divergence constraint means, right? And you want to be able to preserve this divergence constraint in the right way. And so this is the part that applies to other PDEs, right? So if you're solving, let's say, something with liquid crystals where you have a length constraint, then you need to deal with this differently, right? If you're solving elasticity where you have the constraint on the determinant, again, you need to handle it a little bit differently. But the fundamental idea, which is that you need to understand the singular operator, this constraint, that stays. And then when applied to the Navier-Stokes equations, we end up with a solver that is robust in 2D up to Reynolds number 10,000, in 3D up to Reynolds number 5,000. It has linear complexity, good parallel scalability, and I don't think I highlighted this here, but so these problems have over 1 billion degrees of freedom. So we ran this on the UK supercomputer on like 25,000 cores, and it scales well in parallel. And as I said before, there's extensions to other problems. So here on the right, this is a project by a student here, Melody. She extended this to problems for variable viscosity Stokes equations. So you can see here that you have a problem. This is sort of an Earth crust simulation where you have different materials of really extremely varying viscosity and a very highly nonlinear rheology. And you end up with these sort of kind of funky looking solutions that have these faults in the Earth. So if you've ever seen like an exposed face of rock, sometimes you see these faults in it. And yeah, she's been able to scale this to almost 2 billion degrees of freedom. And yeah, there's some other applications that I mentioned here. Yeah, that's all I've got, and I'm happy to take any questions.
Well, thank you, Florian, for this very interesting talk. And now it's time for questions and comments. Questions? Florian, I want to start with some very basic. When you show these quad results with the standard multigrid, what kind of smoothing we're using is Jacobi, right?
Yeah, we just use Jacobi.
And I guess you have the same problem with Gauss-Seidel, I think, right? Something similar because of this diagonal situation.
Yeah, exactly. So the Gauss-Seidel helps you to deal with the advection better, but it doesn't really help you to deal with the singularity from the gamma div u div v, right? So where did I have the PDE? So the Gauss-Seidel doesn't help you with this term.
Yeah, of course.
But for example, we can, so the solver we wrote, if you have these little patches and you solve on them, you can do that in sort of a Gauss-Seidel way where you solve for one patch first and then for the next one and then the next one, and you solve them one after the other instead of all at the same time. So there's this analogy of, some people call it additive versus multi-applicative smoothing. You can still do the same thing, and it helps you with the advection. But the key for this term is having the larger subspaces. Okay.
This leads me to another question. This robust smoothing that you propose is very, as you said, space dependent, right? So it's very dependent on the finite elements you're using.
Yeah.
I'm just curious, maybe I lost that, but when you have these very complicated spaces, this is not provoking complicated versions for the stiffness matrix, for instance, is not ruining that, because I am thinking, for instance, in the case of highly nonlinear viscosities. Curious to take a look on this paper, because in that case you have a weighted and probably nonlinear stiffness matrix, right? And if you have these very complicated spaces, probably you have you sum up a complication. I'm not sure, but probably that is not the case, or.
So the stiffness matrix doesn't of the system you solve doesn't change due to the preconditioner that we choose here, right? So what we do is you pick some discretization, you assemble your global stiffness matrix. This is the system you want to solve. And then what this analysis essentially tells you is what sort of small subblocks do I pull out of the large stiffness matrix to solve, right? So for Jacobi, you pull out just the diagonal.
Yeah, okay, got it.
And we pull out bigger blocks. And then, okay, so this block might be difficult to solve, but it's small. So we then use LU factorization to solve these smaller blocks.
Okay, understand. Understood. I'm clear. Just one more question regarding the prolongation, for instance. Usually, I mean, the textbook prolongation or weighting is bilinear interpolation, for instance, or something like that. But how do you obtain this free divergence for the prolongated function? Is a variation in an interpolation, or how do you do it?
Yeah, so it's again very mesh dependent. So let's start with the easiest case, which is the meshes are nested, right? Then the interpolation is actually an exact operation, right? There's no error induced by this. And so the only thing we need to do is ideally what you want to do is you want to solve a sort of projection problem of what's the closest function to the prolongation that is divergence free, right? But that's, a global projection problem, that's expensive. So what we do is we find these small problems that we solve where you can sort of locally just manipulate the function to become divergence free, right? But if something was non-nested, then yes, you would have to come up with a way of manipulating the standard linear interpolation to enforce a divergence-free constraint. And there's people who do this, and there is sort of specific divergence-free interpolation routines. So for example, you could think of something like you have a divergence-free function, you look at that way, it's the curl of a potential. You apply interpolation to the potential, and then you apply the curl again, and that guarantees you that you're divergence free, right? You can do all these tricks. But we usually use the fact that there's some structure to our mesh hierarchy, and that way we can just use standard interpolation, and then we fix it up with hindsight to ensure the divergence free property. So all of our stuff assumes nested hierarchies, for example. Which is a limitation in practice. Okay,
and just more question, more as a curiosity. Do you have some comparisons between these very complicated spaces in order to see which one is the best? I mean, in the sense that it's not that complicated and still providing good results.
Yeah, so I would say that this method here, so if you do this in 3D, you can pretty easily imagine that these patches are ginormous, right? So you get like 500 or 1,000 degrees of freedom.
Yes.
So I would not propose this for a practical solver. This has really nice theoretical properties, because you can show that the divergence constraint is satisfied exactly. All the error bounds are independent of the Reynolds number. It ticks all the theory boxes, but practically I would never recommend this, because on each patch you suddenly solve a 1,000 by 1,000 in your system, which is very expensive. So I think what in practice what works really well is this version and this version, because it strikes a good balance of you get very good robustness, but you only have to solve in your systems of size like 20, 30, 40, which you can do like very rapidly on a machine. Yeah.
Okay. Good. And the last question. If you want to, I guess you parallelize this. You made it in parallel. I don't know. Usually the discussion is that you need to use Jacobi or Gauss. I think outside it is better for parallelization or something like that. But how do you do it? Sorry, it's like this color system for the.
We don't do any coloring. So the only thing. Okay. So if you do sort of a parallel version of Jacobi, then okay, it's trivially parallel. You don't have to worry about the order or anything, right? Because it's all done in parallel. Now, if you want to do a Gauss-Seidel equivalent of this, essentially what we do is we distribute the mesh in parallel. We do Gauss-Seidel on each core, but globally it's done additively. So globally it's all in parallel, right? So if we had someone, I mean, it would be nice if we had something more advanced than that. But I mean, we found that Jacobi works pretty well, and doing any extra sort of advanced parallelization of Gauss-Seidel, it would improve things, but it's just a huge amount of effort in sort of a very general 3D parallel code.
Okay. Got it. Thank you, Florian. Are there more questions or comments?
I just have a curiosity. Well, first, thanks for the talk. I was just wondering, for example, when you work with the Stokes problem in an optimization manner and you penalize it with the L2 penalization, you may face this locking problem with the velocity because it tends to 0. So I know you're not dealing with the optimization problem, but with a system penalized. So did you face this kind of problem or not at all?
No, so that's a really good point. And that's where the this in-sub condition that I mentioned at the very beginning comes into play. So the locking is avoided as long as the subspaces that you use for the velocity and the pressure satisfy this condition. So if this is satisfied, then there's no locking.
Okay, thanks.
Juan Carlos, please.
Thank you, Florian, for the interesting talk. I just have a curiosity. Maybe I lost something, but I didn't get the connection with respect to the augmented Lagrangian, actually, because what you did was more related to a penalization. So I didn't see any Lagrange multiplier going on there.
Okay, let me go back to that. So if you ignore this term, if you ignore this term here for a second, right? Then, well, let me go to the weak form. Let's see. Okay, so for the Navier-Stokes equations, or let's just think of the Stokes equations, we minimize this energy subject to a divergence constraint, right? So the standard Stokes equations are just the Lagrangian form of this minimization problem with the constraint, right? Where this is your constraint, and this is your Lagrange multiplier.
Okay.
So that's the standard Lagrangian approach to solving an equality constraint optimization problem. And now, okay, what does the augmented Lagrangian do? The augmented Lagrangian adds the penalty term to the Lagrangian formulation, right? And so for what that corresponds to here is this plus gamma div u div v. So in some sense, the standard way of solving Stokes or Navier-Stokes is you include a Lagrange multiplier for the divergence constraint. And the augmented Lagrangian part here is you also include this penalty in the formulation. And and it's exactly what you see when you do augmented Lagrangian problems in optimization, right? So if you make this penalty parameter really, really large, then solving the intermediate problems in the augmented Lagrangian becomes really difficult. But if you make the parameter too small, then enforcing the constraint is harder.
Okay, okay. So you use the, okay, I understand. So in the energy formulation, you don't have the Lagrange multiplier, it's implicitly in the space and is your pressure, right?
Yeah.
Concerning the penalization term, so it's just a quadratic, did you test something else?
No, we didn't do anything else. The nice thing about this quadratic is that once you differentiate and you have the optimality conditions, it's a nice bilinear form that doesn't change throughout the optimization, right? So if we were doing something like some exponential of div u or something, then at every step you'd be adding a different matrix to your system, and I think that would complicate things.
Okay, thank you.
Thank you. Do you have more questions or comments, anyone? Okay, if it's not the case, thank you again, Florian. This was a really interesting talk. Probably we will contact you within these days, because there are a couple of very similar subjects going on here. So probably we can discuss a little bit more. Thank you
again for having me.
Yeah, thank you. Thank you all for coming, and I'll see you in next week, actually, for the next talk. Thank you, Florian. And as I said at the beginning, you are always welcome. I know that many people get very frustrated because of the IFIB didn't take place here in the city. So please, you're welcome as soon as you can come. Of course, we will be happy to receive you here.
Thank you. That sounds fantastic.
Thank you all, and have a nice weekend.
Bye.
Bye.
Bye, everyone. Thanks.